you guys are here. I guess you're wanting me to teach? I'm sorry. I just don't feel like myself. I've been really stressed out recently. And you know, all this pressure, this is just our second day of class, and you're probably expecting such great things. And now, all I got is some blank paper. I don't even know where to start. I feel like you might as well just keep on watching music videos or something, and for all it's worth, we just got blank notes, we got nothing. I don't even know where to begin sometimes. What's that? Oh, I should start with learning objectives? Is that what you said? Oh, that's a great idea, Steelio. You always know the right things to say. Well, what kind of learning objectives should they have? I wrote them down? When did I do this? Oh, sometimes. Oh, it seems I do have some learning objectives. Let's see. Define and explain engineering stress and strain. And then draw a typical stress-strain curve for ductile metal and describe the different regions. And then determine basic engineering properties using stress-strain test data. Oh, that'll be perfect. You can't even see them? Go figure. They can't see it. They can't see it, Steelio. Just go ahead, take a look at your paper. I think they're on there. They should be on the first page of your notes. All right, Steelio, you're right. I do feel better now that we have learning objectives. But sometimes, you know, the stress just gets to you. What do you do when the stress gets to you? What do you do when the stress gets to you? Well, I don't know what you do. I can't hear you right now. But, you know, I do know that at Angelo State University, I believe you can contact the university health counseling services located in the university health clinic, and they'll help you. They'll help you get to the resources you need. You can go to their website and you can get the numbers to call them. And even if their office isn't open, I heard you can contact the ASU campus police, and they'll direct you to the counselor on call. So you always have access to that as a student if you're feeling really, really stressed out. I don't think I'm quite at the breaking point, but I do feel a little bit stressed. And so I feel like I really just need to talk to a friend. Can I talk to you guys as my friends? Well, maybe. I hope to be friends with you guys. But I know Steelio, my friend. He's gonna help me through this. Steelio, what do you do when you feel like you're stressed out and you're just going crazy? You feel like you're being pulled apart at both ends and you're just gonna snap. What's that? Oh, he said we should draw a free body diagram. All right, let's see if we can do that. All right, so let's just imagine just a general object. I'm gonna take just this rectangular block here. And what if we pull on that, right? Let's go ahead and draw a free body diagram of this simple case. All right, so we got engineering, stress. You can go ahead and put this in on your notes, right under the learning objectives. We need to draw a free body diagram. Let's work on our drawing skills here. We'll get that block in 3 dimensions. Now we'll draw some forces on it. So we got a force, say a load of P in both directions. All right, that looks like a pretty good free body diagram of the case we just looked at. But Steelio, I feel like we can't just look at objects and talk about the force acting on the objects. Because look, I mean, I know like you're little bitty, but you're strong. But if we compare you to like a giant beam or something on like a bridge or a building or something that has a lot more steel than you, it's gonna definitely handle more force, right? I'm right. Okay. Well, how do we handle that? How do we make it fair? How can we compare you to like this bridge beam? Because you're the same material, right? Steelio says we need to look at the amount of material and compare the two material amounts. So how can we do that? Well, one way is to look at the area that's resisting the force. So in Steelio, that would be this area right in here. Perhaps in our block, it would be the cross-sectional area right here. So I want to go ahead and look at the area. And so it has some sort of area of our block, and we'll call this area, the initial area, A0. And we say that engineering stress is defined as the force per unit area of the member. So depending upon how much area you have, that might dictate how much force you can handle, especially if you're talking about the same materials. Force per unit area is going to be our term for engineering stress. Our symbol is going to be the Greek letter sigma. So this is sigma, and it's going to equal our force per unit area. And in engineering stress, we're going to use the initial cross-sectional area. All right, well, that's seeming to make sense. It seems like that's a fair way of comparing you to the girder. And then, maybe stress is a good way of comparing different materials, because I know, like, right now I'm feeling super stressed out, right? And I know if I was being pulled, I would probably not handle nearly as much force as you, Steelio, because you're steel and you're great. I'm right? Yeah, so you can handle higher stress because you're a stronger material than just my weak body, right? Good. Oh, I think I'm starting to understand this engineering stress thing. I hope you are too. Anyhow, Steelio, just sometimes it's not just the stress of things, right? Sometimes it's just like how many things you have to do. Like, I just schedule all these little things. I have meetings here, meetings there, and you just got, you feel like your schedule is pulling you apart, like you're just so strained by having too many things to do. How do we handle that? What's that? Oh, it seems like we have another engineering term for that called strain. Well, let's talk about engineering strain. All right, engineering strain is not just like, the fact that you have a lot of force or big things happening to you. It's just you have so many and it's almost like you're being stretched too thin. It's kind of that like strain. That's what we're talking about, that stretch. So let's go ahead and take a look at how we look at stretch on this member, right? This was the one we drew the free body diagram for. So when I pull on this, I think you can see it's going to extend outward. So let's go ahead back to our free body diagram and let's draw that extension. Right? I imagine it's going to stretch out some due to the applied force that I have on the object. And this is going to be the amount of stretch that I undergo. This is going to be my change in length of my object. And if this is my change in length, then my original object has to have some original length. And so we'll refer to that original length as L0. So that'll be the initial length. And so it seems like we can look at this change in length and be able to determine something about strain. But again, that doesn't really seem fair, Steelio. Do you have an answer for this? Because like when I take a look at like this bridge and I see all these different cables, right? I see like some cables that are very long and some are shorter than others, right? And I think kind of like this bungee cord, that if I was to apply some force, say I apply 10 pounds to the bungee cord, it's going to stretch a certain amount. But if I apply 10 pounds down here at the bottom, I expect more stretch. So even though it's the same chord, but because the length changed, it seems like I can't just compare delta L. Is that true, Steelio? Oh, he's right. I'm right. I do have to take into account that initial length. So we're going to kind of like stress where we normalize by the initial area. We want to take strain and we're going to take this amount of stretch but normalize it by the initial stretch. All right, let's go ahead and come up with a definition for that. So it seems like engineering strain is going to be change in length relative to the initial length. So if we're going to give that a formula, we're going to use for strain, we're going to use the Greek symbol epsilon. So this is, working on our Greek alphabet. So we have epsilon. Epsilon is going to be the change in length, which is delta L, over that initial length, or normalized by the initial length. So that gives us a formula for strain. We can also rewrite this as saying the final length minus the initial length over the initial length. And so this gives us, some measure of strain, and we see if we're stretching like we were in our example, then this becomes a positive number, so that's positive strain. But if we're compressing, our final length is smaller than our initial length, and so we'll get negative, and negative strain just means compression, as we're going to take it for our sign convention. Also, we see that we continue to always normalize by that original length. So we're not going to update the length, we're always going to use the original length. And that's how we define engineering strain. Just like engineering stress always refers back to the original cross-sectional area. Sometimes it's a little bit of a weird value, so we might want to express this as a percent. So we call it the percent elongation, and it's just the strain times 100%. So this tells us if the percent elongation is 25%, then the object got 25% larger. So that's what's represented here. So strain is kind of unitless. If we multiply it by 100%, we kind of get this percent elongation. And that helps us just think a little bit better about strain. Whew. I really think we're getting somewhere here with this engineering stress and the engineering strain. And I hope you guys feel like you can achieve this first learning objective to be able to define and explain engineering stress and strain. All right, Steelio, we need to talk a little bit more to you. How do we determine this for different materials? Like, I just feel like we could get numbers that are all over the place. Oh, that's very interesting. Steelio tells us that they kind of have a standard test so that we can test different materials so we can determine how much stress and how much strain these materials can take. And so he says it's a universal testing tensile test. That's the standard thing. So let's go ahead and put that up. It's the uniaxial tension test in a universal testing machine. I know, the nomenclature gets crazy. So I want to talk about the uniaxial tension test. All right, so what do we know about this, Steelio? Can you tell us anything? Just look at you? Oh, you want me to draw a picture of you. Okay. Oh, that's one of my favorite things to do in life. Let's see if we can draw a picture of Steelio here. All right, that looks pretty accurate, right, Steelio? Yeah, I think so. All right, so Steelio tells us that he is an example of a test specimen that we could use to perform a uniaxial tension test, especially if we are looking to determine the properties of the steel that he's made out of. And so he has some sort of narrowed down. Do you think for a second, why would we shave Steelio down in a little bit in part? Thinking. All right. Hopefully you thought of a good answer, but you should have realized that when we pull this apart, right, we want to control where the failure happens. And so we have this smaller cross-sectional area through here so we can control where that failure occurs. So anyhow, we're going to put him into our tension test and pull on him just like we looked at that free body diagram. And as we pull on him, we're going to watch him stretch. Now, we know that failure will happen somewhere between here and here because that's the reduced cross-sectional area. So this is what we would then determine is the initial length of our specimen. And then somewhere in here, we would have the initial diameter, and that would then be able to help us calculate the initial area. So these are some of the properties we'll need to know before we run a uniaxial tension test. And then he says that we can go ahead and we can run this test, and this is going to give us some data. And he says this test is a standardized test, so we should go ahead and put that in. Standardized test by our friends at ASTM International, the American Standards of Testing and Materials, ASTM, and they have a standardized test that relates what we'll call the P delta behavior. So P delta, and I'm going to use little delta here, P little delta behavior of material. And if we follow the standardized test with all the dimensions, standard speeds and everything, we'll be able to compare materials to one another. All right, so we have the initial things, and we're going to get what the P delta behavior is. Now this delta is just like our delta L, and it's going to be in the direction of P. So as we pull on this specimen, Steelio is going to get longer. So we're going to measure this displacement that occurs. All right, so we do this, and we run our test. Voila, we get some test data. And we're going to then want to plot our P delta response for the material. And so that's going to give us kind of how this material responds, this particular specimen. But we said that this isn't fair, right? We can't compare materials by force and delta. We really need to use our engineering stress and our engineering strain so we can compare the materials fairly to one another. And so from this test data, we'll be able to, what we say, normalize our test data, and then we'll obtain, what we ultimately want to obtain is our stress versus strain data for the specimen. All right, so this is what we're after. We're after getting stress and strain data for our materials, using our formulas for stress, using our formulas for strain to make these calculations. So we can do all these calculations at various levels of magnitude of force. We can measure the displacements. We'll get all this test data. We can do all the calculations, and then we'll have kind of our standardized curve for the material. Thanks, Steelio. I no longer feel so stressed out about this class anymore. I'm starting to feel like my old self again.